We are now going to check this transceiver for spurious emissions and their levels. This is a requirement from the ACMA. Under the conditions for every amateur license, the ACMA specifies the maximum amount or level of the spurious. Here from their publication it says the spurious have to be less than minus 50 dB or less than 43 plus 10 log PEP. If it's 10 watts then it becomes minus 53. The spurious have to be the smaller of the two, and I'm assuming here minus 53 is a smaller spurious than minus 50. If you're running 5 watts it's minus 50 dB, if you're running 2 watts it's minus 46. So I've set up my test equipment. I have the transceiver fed into a dummy load. It happens to be part of my antenna tuner, which also has a SWR and power meter and also an oscilloscope. I'm going to use the AM mode because the carrier is nice and steady, so I'll just select that on my panel. There it is there. I'll just zoom in a little bit closer so you can see the mode I've selected. There it is down there, and I'm going to use 7.150 megahertz. To measure the level of spurious and their frequency we need a spectrum analyzer. So here I'm using the oscilloscope in the FFT mode. I'll just turn the transmitter off. It's running 10 watts. There's a little spurious there. That's coming from the oscilloscope's picking something up somewhere. The transmitter's off. And there we have the transmitter on, and you can see a little pip up here. That's an image of the transmission. This transceiver uses a 455 kc IF, so there will be an image at twice the IF away, which happens to be 910 kilohertz above the output frequency. And as you can see from the display, this little image is at around 50 to 50, let's say 53 down. It's around 53 dB and it's bouncing up and down a little bit. So that's the spurious. I can't really find any level of harmonics, so that's about all I could see there. And there is the same 7.15 megahertz signal on the analog crow, just so we can see the sine wave. That's a view of the power meter on the antenna tuner, which is switched to dummy load at the moment, and just see I've got it set to the 10 watt range. There's 10 watts, so it was just sitting there. I'll just drop it down for a moment. If you don't have a spectrum analyzer, there is another way to check your spurious using another receiver. I'll just show you that. I'm going to use the IC706, and the S meter on the IC706 is an indication of the level of the image. So there's the signal on the IC706. I'm getting around a 1 kc beat note. It's quite strong, so I'm going to switch some attenuation in so the S meter isn't reaching the absolute maximum. It's reading 40 dB over S9. That's at the 10 watt level. Before we go looking for the spurious at twice the IF, we need to know exactly where to look. Now this is a block diagram of the transmitter portion of this transceiver. Microphone with a 1 kc tone, a BFO which mixes with the audio to produce a lower sideband, produce a double sideband signal at the output of the balanced modulator. That passes through an LSB filter, and you'll notice we're actually at this stage we're getting an upper sideband signal. We then have to transmit that signal on the 40 meter band, so we've got to mix it up using the VFO. The VFO is on the high side, so we get what's called inversion, sideband inversion, because we're on the high side. And here at the output of the transmit mixer and the buffer amplifier, we now find we're on lower sideband mode, and we'll also find the image and the harmonics. At the output of this amplifier we pass through some band pass filters which are tuned for the 40 meter band. These filters are quite sharp, and they result in a reduction in anything outside the 40 meter band. For example, I found the image at minus 45 dB. We have an additional attenuation of that image in the low pass filter that feeds the antenna after the power amplifier, and that's where we're getting our minus 53. The low pass filter has around about a 10 dB drop at the frequency of the image. There is a plot of the low pass filter after the power amplifier. The image is around here. It's just above 8 megahertz, and it should be around about 8.5 dB. I found it's a little bit more than that. A quick calculation. We're transmitting on 7.150. 910 is twice the IF away. We up the band, and we should be looking at 8.06 megahertz to see how strong that image is on our receiver. This is not a bad test actually, because this is the signal that someone will hear when you're transmitting. If they're listening to your signal at 40 dB over S9, how strong will this image be? So we're going to tune up there and have a look. So there's the main signal, 40 dB over S9. I can't say these meters are great, but it'll be good enough for what we're trying to do. So we'll now tune up to 8060 and see what we hear up there. This transceiver is actually going into a dummy load, and there it is there. I can just hear it. Now you'll notice I've got the attenuator on and no preamp, because otherwise I would be well over S9 plus 40. There's nothing there. So we're well and truly below the minus 50, I would suggest. This is what someone would hear if you're 40 dB over S9 on their receiver. If they tuned up to this part of the band, that's assuming their antenna has an equal response up there than it does down at 7 megs. It's pretty unusual. Most amateur equipment will consist of a dipole, and the dipole will be reasonably sharp over the 40 meter band and won't have anywhere near as much gain up at 8 megs. And that would assume that they are listening at 8 megs and not on an amateur band. In other words, they may be just tuning around on a receiver of some sort. I've decided to use the IC706 rather than my homebrew gear, because this is a commercial product and we expect the S meter reading to be reasonable. I wouldn't say it's perfect, but it's reasonable. The output of the transmitter band mixer that pushes the signals up into the amateur bands feeds some filters. I've got a set of filters for 80 and a set of filters for 40. This is the circuit diagram I'm using. This filter has to be very well adjusted in order for you to get that image down so low. If you don't adjust this correctly, the image could be quite strong and you may not meet the minus 53 dB at 10 watts. Here's a closer look at the circuit of the filter. It's just two parallel tuned circuits with a top coupling capacitor. The top coupling capacitor determines the overall bandwidth of this filter. I can cover around about 200 to 250 kilohertz on both bands within a dB or so. Past those frequencies, then things start to fall off quite quickly. This is a view of the 40 meter filter. It's on the bottom of the case. There's the two tuning capacitors and the top coupling capacitor. I think that's around about 10 pf, that small trimmer, and it's set about halfway, and there's another 10 pf in series with it, so that in effect we're looking at about maybe 4 or 5 picofarads. You don't need much in that coupling device. It's a few pf is enough to give you the 200 kcs. You adjust these two coils, these two trimmers. The way I do it first is set the trimmer halfway, the coupling, then I tweak both of these trimmers for a peak at the middle of the band, like for example 7.1 megahertz, and then I start to tweak each of those somewhere, one down the bottom of the band at 7050 and one at 7155, and I found that works reasonably well. It gives you a pretty flat response, and then when you go and check the image you'll find that that's quite good. If you happen to tune one of these coils too far up the band, for example at 7.5 megahertz by accident or whatever, you'll find the image won't be minus 45, it'll be maybe minus 30 or something like that. Here you see the other filter, that's the 80 meter one. The 40 meter one switched on at the moment because I'm doing this test on 40. I found the image at 40 meters is just as good as it the image at 80 meters just as good as at 40 meters. Maybe not quite as down, but well within the minus 50 as far as the receiver is concerned. That's the 10 watt PA up there, and there's a 1 watt PA, 1 watt driver down here. So that's a bit of a look in the bottom. There's a wider view. We can go down a little bit closer. See lots of bits and pieces there. The 1 watt stage is this one here with the little heatsink, and there's an IRF 510 transistor in there with a little bit of a heatsink on it. And there's the 10 watt PA. It's actually around about a 30 watt, but I'm not pushing it to 30. I'm just limiting it to 10 watts. I've got a form of ALC control on this rig that limits your power. It's part of the SWR protection. Here's a test on the 80 meter band. I'll just show you what the image is like from on that band. I've just set the transceiver to 3.6 on the AM band, and I've got the IC706 tuned down to 3. There's the IC706 on 3.6, and we are getting 40 over. I'm just tuning the rig, the homebrew rig. There you go. Now I'll go to now that other frequency. The image should be at 4.510. 4.510. Turn the volume up a bit. 4.51. There it is. So again, there's nothing on the screen. Just turn this off. There you go. So the idea of these images is that, of course, they're not on the amateur band, but then they're also possibly on bands that other users are using. So no one wants you to transmit on top of them outside the amateur band. So you have to make sure these images, or these spurious, are low enough not to cause interference. So that's it for now for the spurious emission test.